Welcome to AP Biology. This video is on the structure and function of carbon within organic molecules. Carbon is an element that is central to life. Our central question is, how does carbon lead to diversity in life? The answer lies in carbon's structure. Carbon displays what we call tetravalence. Tetravalence means that it has 4 valence electrons. Here you see 1, 2, 3, 4, which means that carbon is able to bond with 4 other atoms. This ability can create a wide array of different organic molecules that have different shapes. The shape of a molecule is going to give rise to its properties and to its functions. The branch of organic chemistry studies compounds that contain carbon. What role does carbon serve within an organic molecule? It forms the core or the central part of an organic molecule called the carbon backbone. You can see by looking at these pictures here that the carbon backbone is going to determine the shape or the structure of an organic molecule. Its shape or structure is going to give rise to its properties or to its functions. You can see that you have linear chains of carbon. You can have branching chains of carbon. You can have carbon rings, right? You can have double bonds within an organic molecule within the carbon backbone. In biology, we often see hydrocarbons. Hydrocarbons are long chains containing carbon and hydrogen. Since there are so many bonds in a hydrocarbon chain, it contains lots and lots of potential energy. A common organic molecule that contains hydrocarbons is fat. Fat has much more energy per gram than carbohydrates and proteins. It has 9 calories per gram, where carbs and proteins only have 4 calories per gram. The reason that fat has so much energy is because it contains these hydrocarbons, these long chains of carbon and hydrogen that contain lots of chemical bonds, and when each of those bonds is broken, we have a massive release of energy. Here we look at a good example of how structure leads to function. We can look at isomers. Isomers are molecules that have the same molecular formula, but they have a different arrangement of atoms. By having a different arrangement of atoms, they have a different shape, and therefore they have a different function. There are 3 types of isomers. The first type of isomer is a structural isomer. Both of these molecules here have the same molecular formula. They're both C4H10, but in a structural isomer, they have a different arrangement of carbons in the carbon backbone. By having a differently shaped carbon backbone, these molecules are going to have totally different properties. Next, we have a geometric isomer. Again, they have the same molecular formula, different arrangement of atoms. In this case, they have the same carbon backbone, but they have a different arrangement of groups that branch off of the carbon backbone. The groups that branch off of the carbon backbone are called functional groups and are shown in X right here. With geometric isomers, you often have a different arrangement of functional groups around a double bond. In this first geometric isomer, both functional groups are on the same side as a double bond. We call this the cis formation, CIS. When the functional groups are on opposite sides of a double bond, we call this the trans formation. When you hear words like trans fats, a trans fat has the functional groups, the hydrogens, on opposite sides of a double bond. Finally, the last type of isomer is called an enantiomer. It's also called a stereoisomer. Again, they have the same molecular formula. In this case, they are mirror images, or left and right hand images of one another. Although they appear very similar, because they have a different shape, they have completely different properties. Here you see a great example of enantiomers. Here you have two forms of dopa, L-dopa and D-dopa. These are synthetic versions of dopamine, which is used to treat Parkinson's disease. L-dopa is extremely effective at treating Parkinson's disease. D-dopa is inactive. It does nothing. You can see how similar these two molecules are. They are mirror images of one another. They have all the same numbers of atoms. But since they have a different arrangement, since they have a slightly different shape, they have completely different properties. This really shows the relationship between structure and function. Finally, we have functional groups. The functional groups, again, are the groups that branch off of the carbon backbone. They are extremely important because the functional groups are the part of an organic molecule that participates in chemical reactions. If we analyze the two factors that give rise to the properties of an organic molecule, number one would be the arrangement of carbons in the carbon backbone, and two would be the functional groups. Here you see some common functional groups that we'll look at throughout the course. First, you have a hydroxyl group, OH. These are found commonly in alcohols like ethanol. Next, you have a carbonyl group, which is a carbon double bonded with an oxygen. We find these in aldehydes and ketones. Next, we have a carboxyl group, carbon double bonded to an oxygen. The carbon is also single bonded to another oxygen. You can see here that you have a non-ionized and an ionized form of the carboxyl group. Carboxyl groups give up, they donate hydrogen ions to solution. Therefore, they are acidic, right? They're an acid. Carboxyl groups are found in carboxylic acids. When we look at organic molecules, we're going to find that amino acids contain carboxyl groups, and that's why we call an amino acid an amino acid. It's acidic because its carboxyl group donates hydrogen ions. The amino part of an amino acid is due to the amino group. The amino group is NH2, which can also ionize and become NH3 positive. So it accepts hydrogen. Since it accepts hydrogen, it would be a base. When you look at an amino acid itself, it's neither acidic nor basic, it's neutral, because you have one half of it that's going to donate the hydrogen and the other half of it that's going to accept the hydrogen. Sulfhydryl groups are made up of sulfur and hydrogen. We will not see them often. And a group that we'll see very often is the phosphate group, which is a phosphorus that is bonded to 4 oxygens. And you can see that these oxygens both have negative charges. We're going to find phosphate groups in ATP, GTP. We're going to see them in nucleotides, or the building blocks of nucleic acids, DNA and RNA. We're going to see many, many phosphate groups in this course. Phosphate groups are extremely rich in potential energy. This concludes this video. Thank you.